Picture this. You're on a train, comfortable seat, coffee in hand, completely relaxed. Outside your window, nothing, not darkness, not a tunnel wall, just nothing because you stopped paying attention 10 minutes ago. You're scrolling your phone, maybe eating something, and 78 meters below the surface of the ocean, moving at 250 kilometers per hour through solid rock, you are completely unbothered. Above you, container ships the size of skyscrapers are crossing one of the world's busiest shipping lanes. The water pressure at your depth could flatten a car like a piece of paper, and you don't feel any of it. That's not a scene from a movie. That's what commuting looks like in China starting 2028. But here's the thing. This tunnel, as insane as it is, might not actually be the real goal. We'll get to that. First, let's talk about how you build something that most engineers thought was borderline impossible. Zhoushan is an archipelago off the eastern coast of China, over 1 million people, one of the country's largest fishing industries, a massive offshore petrochemical complex that handles a significant chunk of China's imported oil, strategically critical, economically active, and for most of its history, completely cut off from the mainland's rail network. You could get there by ferry. You could drive across a series of bridges completed in 2009. But high-speed rail, the kind of connection that actually integrates a place into a national economy, that required something the bridges couldn't provide. It required going under. Not under a river, not under a shallow bay. Under the open ocean floor, 78 meters deep, through some of the most geologically unstable marine sediment in the region. China looked at that problem and decided, let's build a high-speed rail tunnel. And not a slow, cautious, take 2 decades kind of tunnel. A fast one, an aggressive one. The kind that, when it's done, makes every other country look at their own infrastructure plans and quietly reconsider what they've been calling ambitious. The Jintang Undersea Tunnel. Total length, over 16 kilometers. Section running beneath the actual seabed, more than 11 kilometers. Deepest point, 78 meters below sea level. Train speed, 250 kilometers per hour. Now, before we get into how they built it, and the how is genuinely extraordinary, there's something you need to understand about why this specific project matters beyond just connecting 2 places. Because this tunnel is a message, and some people are reading that message very carefully. But we'll get there. The machines first. Because without understanding the machines, nothing else makes sense. Tunnel boring machines, TBMs, have been used in major projects for decades. The Channel Tunnel used them. Projects in Japan, Norway, Switzerland. TBMs are not new. But the 2 machines built for the Jintang project are not your standard TBMs. They were named Dinghai and Yongzhou. Each one is approximately 150 meters long, that's roughly half the height of the Eiffel Tower, laid on its side and pointed into the earth. The cutting head at the front, the spinning disc that actually grinds through rock, is nearly 15 meters in diameter, 5 stories tall, rotating with enough force to move through solid granite. Each machine weighs around 4,000 tons, the same as 8 fully loaded 747 jets, and they don't fly anywhere, they crawl. 10 to 15 meters a day on a productive stretch, slowly, relentlessly, eating through the seabed 1 meter at a time. But the size isn't the impressive part. The impressive part is what they do while they move. As the cutter head grinds forward, the machine simultaneously removes all the excavated material, installs precast concrete ring segments to line the tunnel walls, and injects grout into the gap between the rings and the earth to seal everything watertight. It's building the tunnel as it digs it, an autonomous underground factory moving in one direction, never stopping, constructing the corridor behind itself as it advances. And this is happening 78 meters below the ocean, in complete darkness, under pressures that would destroy most engineering systems not specifically designed for this environment. Now here's where the geology becomes a problem, and I mean a serious problem. The tunnel route passes through what engineers call mixed geology. That term does not do justice to what the machines actually encountered. Over the course of the tunnel's path, Dinghai and Yongzhou hit 28 distinct geological transitions. 28 times the ground changed character significantly enough to require a completely different approach. Solid granite, hard, stable, predictable, but brutal on the cutter teeth. Then suddenly soft marine clay, Water-saturated, unstable, the kind of material that collapses if you remove support faster than you install it. Sandy sediment deposited over centuries by ocean currents. Layers of rock interspersed with pockets of material that behave almost like liquid under pressure. Each transition is a potential disaster. Move too fast through soft ground and the tunnel face destabilizes. Apply the wrong pressure and water finds a pathway in, not a drip. A flood at full ocean pressure from 78 meters up. The engineering team modified both machines specifically for this environment. Water injection systems on the cutter head to prevent clay from caking onto the blades. Reinforced sealing systems around the main bearing, the most vulnerable point on the entire machine, redesigned to handle sustained water pressure at depths no standard TBM was ever certified for. Real-time sensor systems feeding geological data forward to the operators so they could adjust speed, face pressure, and grout injection before a transition became a catastrophe. These weren't tweaks, they were fundamental redesigns of how the machines operated. And they had to work every single time because 78 meters below the ocean floor, there is no such thing as a small mistake. But the geology was only half the problem. The other half was mathematics. And this is where the project stops being just an engineering challenge and starts feeling like something else entirely. The tunnel was bored from both ends simultaneously. Dingai launched from the Zhoushan side, boring approximately 6,000 meters. Yongzhou launched from the Ningbo mainland side, boring approximately 5,000 meters. Somewhere in the middle of the seabed, in complete darkness, surrounded by ocean, they were supposed to meet. Not approximately meet, not close enough. Meet. With the kind of precision where the walls of one tunnel align seamlessly with the walls of the other, the track can be laid in a continuous line, and a train doing 250 kilometers an hour never feels the junction. Think about what that requires geometrically. Two objects starting 11 kilometers apart, converging toward each other through rock they cannot see through, guided from the surface by people who cannot directly observe them. A deviation of half a degree at launch translates into misalignment of dozens of meters by the time you're 5 kilometers in. And at that depth, you cannot stop and resurvey. You get one shot. China's answer was Beidou, their own satellite navigation network, the equivalent of GPS, but built and operated entirely by China. Standard Beidou positioning is accurate to around 3 to 5 meters, fine for a car. Catastrophically imprecise for this application, so engineers developed a differential correction system using 6 dedicated Beidou satellites feeding data directly into the navigation computers on both machines. The system tracked each machine's position in 3 dimensions: latitude, longitude, depth, updating continuously and comparing the actual path against the planned route in real time. Any deviation, even a single centimeter, triggered an automatic steering correction to the cutter head. Satellite signals from 20,000 kilometers above the Earth, guiding machines buried 78 meters below the ocean floor to within 2 centimeters of a predetermined meeting point. When Dinghai and Yongzhou finally broke through the last rock barrier between them, the alignment error was less than 2 centimeters across an 11-kilometer bore. The Channel Tunnel, when its machines met in 1990 and the world celebrated it as one of the great engineering achievements of the century, had an alignment error of about 36 centimeters. China just beat that by a factor of 18. And then comes the question nobody thinks to ask until someone points it out. The machines are stuck. There's no exit ahead. They filled the space behind them as they moved. You can't reverse 4,000 tons of machine back through 11 kilometers of completed tunnel. So what happens to them? They stay. But not intact. Engineers executed what's called a shell-shedding procedure. Working from inside the machines, crews dismantled and removed every recoverable component. The drive systems, hydraulic mechanisms, the cutter head itself, all the valuable parts, and hauled everything back through the tunnel. What remained was the outer steel casing, the skeleton. And that skeleton stays in the ground permanently, becoming a structural element of the tunnel at the junction point where the 2 bores meet. The machines don't just build the tunnel, they become part of it. Their bodies are embedded in the walls, built in forever. There's something almost cinematic about that. Machines designed for a single purpose, executing it perfectly, and then dissolving into the thing they created. Finishing work begins after tunneling completes, projected for end of 2026. Track laying, electrification, ventilation systems, emergency infrastructure, lighting, communications, everything that turns a reinforced concrete tube into a functioning high-speed corridor. Target opening, 2028. When it opens, Ningbo to Zhoushan drops to 30 minutes, a journey that currently takes over an hour by ferry or road, done in less time than it takes to watch half an episode of anything, 78 meters below the ocean, at 250 kilometers an hour. But here is where the story actually begins, because this tunnel isn't really about Zhoushan. Let's talk about what it's actually about. China has built 45,000 kilometers of high-speed rail, more than the rest of the world combined. They've laid track across the Tibetan Plateau, through earthquake zones, over wetlands and mountain ranges and river systems that engineers in other countries looked at and said, not viable. China built through all of it. The ocean was the last physical frontier, the one category of obstacle that hadn't been fully conquered at high-speed rail scale. The Jintang Tunnel closes that frontier, and when you close the last frontier, you stop proving you can do things. You start signaling what you're planning to do next. Look at a map. Taiwan Strait, the body of water between mainland China and Taiwan. At its narrowest point, approximately 130 kilometers, roughly 8 times the length of the Jintang Tunnel's undersea section. The geology is significantly more complex, active fault lines running through the strait, the result of tectonic collision that's still ongoing. Water depths are variable, with large sections in the 50 to 70 meter range but with deeper channels. Currents are strong and dynamic. And then there's the political context, which is complicated in a way that the phrase complicated almost can't contain. Chinese engineers and state-affiliated research institutions have been studying the feasibility of a Taiwan Strait fixed crossing for decades. The technical literature exists. The surveys have been conducted. The academic papers have been written. And the consistent conclusion is technically achievable, brutally difficult, extraordinarily expensive, but achievable, using technology that either already exists or is being directly developed right now, in real time, by the Jintang project. Because everything the Jintang Tunnel required, high-pressure seabed boring at significant depth, ultra-long-distance precision navigation for converging machines, adaptive operation through mixed marine geology, large-scale logistics for extended undersea construction, all of it scales, not easily. The jump from 11 kilometers to 130 is not linear. The challenges compound, but the capability that made Jintang possible is the same capability that makes a Taiwan Strait crossing conceivable in a way it simply wasn't 10 years ago. Whether that project ever gets built is not primarily an engineering question anymore. That question has been answered. It's now a political question. And political questions about the Taiwan Strait are among the most consequential on the planet. Taiwan's government has shown zero interest in a fixed link, understanding clearly that infrastructure is not neutral, that a tunnel connecting Taiwan to the mainland fundamentally changes Taiwan's strategic position in ways that go far beyond transportation. The United States and its Pacific allies watch Chinese infrastructure capability with the same analytical framework they apply to military capability, because at this scale, the two are not entirely separate. A nation that can build a precision-navigated high-speed rail tunnel under 11 kilometers of open ocean is a nation whose logistical and strategic reach has meaningfully expanded. That's not an exaggeration. That's how strategic analysts read infrastructure projects. And here's the broader point. Infrastructure is leverage. It has always been leverage. The Roman Empire understood this. Paved roads through conquered territory didn't just move soldiers, they moved authority. Modern China understands it too. When you connect a place with a tunnel, with a rail line, with a bridge, you don't just move passengers, you create dependencies, economic integration, movement of capital and workers and goods that becomes embedded in how people live their daily lives. Separation, in every practical sense, becomes progressively harder. China's Belt and Road Initiative, its domestic rail network, its record-breaking bridges, and now its undersea tunnels are all expressions of the same underlying logic. The country that builds the infrastructure shapes the relationship, and China is building faster, at higher technical difficulty, and at greater scale than any other country on Earth right now. That's not national pride talking, that's the data. there are legitimate concerns worth naming. Undersea boring disturbs marine ecosystems in ways that take years to fully understand. The Zhoushan region has significant active fisheries. The long-term seismic risk of operating a high-speed rail tunnel through a geologically active seabed is a real engineering management challenge over a 50 or 100-year operational lifespan. And large infrastructure projects at this scale involve land acquisition, community disruption, and social costs that don't show up in the engineering papers. The extraordinary feat headline always sits on top of a more complicated human story. That's true here too. The economic model enabling all of this is also worth being honest about. China's construction pace is inseparable from its political system. Centralized planning means a decision to build under the ocean gets executed without the decade of review, legal challenge, and political negotiation that equivalent projects face in democratic systems. State-owned firms can be directed onto projects at below-market terms. State banks provide financing that private capital markets would never accept for these risk profiles. That is a genuine structural advantage in mega infrastructure, one that democratic systems cannot simply replicate. Whether that advantage justifies the broader trade-offs embedded in China's system is a question that goes far beyond this video. But it's the honest context for why China is building things other countries aren't even seriously proposing. What's happening with the Jintang Tunnel is the latest data point in a deliberate compounding national strategy to make the impossible routine. Each project generates expertise and manufacturing capacity that feeds directly into the next one. The machines get more precise, the navigation systems get sharper, the construction teams accumulate institutional knowledge that no textbook can replicate. Costs come down, ambitions grow. The Jintang Tunnel is the hardest thing China has built in this specific domain. What comes after it will be harder, and the trajectory suggests they'll build that too. The question the rest of the world is quietly trying to answer isn't whether China can do this anymore. It's where they point this capability next, and what that means for everyone else when they do. If this hit the way I think it did, drop a comment. Where in the world would you build an undersea tunnel if cost and politics weren't a factor? I'm genuinely curious what people come up with. Like the video if you want more of this, subscribe if you're not already, and the next one is worth sticking around for.